So this lecture I'm going to talk about DRAM memory organization. So in our systems, the main memory is designed using DRAM, dynamic random access based memory, right? So how this DIM will be organized and how it is going to supply the data to the processor and what is the mechanism that is used. So those things are the main the components of this lecture. So if you see here inside the CPU tower, right, or even your laptops. So if you open, so on motherboard, you'll have some set of DIM slots, dual inline memory module slots. So if you see here, there are 3 DIM slots which are under the control of memory controller MC. And in each DIM slot, we are going to put a DRAM based DIM, dual inline memory module. So which is basically both sides, you have pins at the bottom. On both sides, these pins will be there, and through that, we will be reading the data. And the entire memory is organized in terms of set of the devices here. You can see the small chips on each side of this DIM, and those are called as the DRAM devices. And within that device, there will be set of subbanks, and each subbank is organized as a set of DRAM arrays. So basically, what we have, the entire DIM is, it consists of set of ranks, logically organized as a set of ranks. Multiple ranks will be there, and each rank consisting of multiple banks, and banks are distributed across multiple DRAM devices. And in each device, we have sub-bank. That means a bank is divided into a set of smaller banks, which are called as a sub-banks. Let us say a bank is distributed across 4 devices, and each device is now holding 1/4 of that particular bank. And there are several such sub-banks will be there inside a device. And each device, if you see, will be consisting of, within that sub-bank, will be consisting of set of DRAM memory arrays. So X2, this particular example, whatever I've shown here, is consisting of X2 device, which is basically 2 DRAM arrays are placed. And it can be X4, 8, or 16, and so on. So once we have this X2 device, let us say, and when we send the address to the DRAM memory, that means like when there is a miss in the last level cache, the request will be sent to the memory controller, and memory controller converts this request into DIM understandable commands, and where it is also going to send the address. But this address is actually divided into 2 parts. The higher order bits are representing the row, the lower order bits are representing the column. So once we initially give this higher order bits to the row decoder and we issue RAS, row address strobe, we assert that signal, then this particular subbank is going to take that value into the DRAM decoder, a row decoder, and which is going to activate one of the rows, which is also called as a DRAM page. And the capacity of each single page is typically 4 kilobytes. That means this horizontal line in this memory array, each line holds up to 4 kilobytes of bits, and each bit is represented in terms of charge in the capacitor. So the DRAM cell at the bottom I've given the intersection point of this horizontal line and the vertical line, where we have this DRAM cell. And that DRAM cell, that is nothing but the charge in the capacitor, is going to be accessed using an access transistor. You can see the access transistor connecting this horizontal line and vertical line. And all these horizontal lines are called as the rows, and the vertical lines are the bit lines. So whenever we want to read any data from the DRAM memory array, first we are going to activate one particular row, and the data that is connected with that one row is going to be loaded into sense amplifiers. And sense amplifiers are designed using the flip-flops. And the data is going to be there in the sense amplifiers. And now we'll give the lower order portion of that address to the column decoder, and which is going to select set of lines. And from there, it is going to read the data from the corresponding positions in the sense amplifiers. And that data will be sent to the data buffer, and which in turn send the data to the memory controller. Memory controller sends the data back to the processor. This is what is going to happen inside. The moment there is a miss in the last level cache, we are going to do all these operations and request the DIMM to supply the data, and whatever the data received by the memory controller, which in turn is going to send it to the processor. So here the DIMM is a passive device which cannot do anything on its own, and it needs to be receiving some signals, and the signals will be sent by the memory controller. So effectively, memory controller is the brain here, and which is going to say what needs to be done at what time. And DIMM is just simply implementing those functions. That's it. Okay. So now if we see this entire DRAM based main memory, logically it can be viewed like something like this. Set of channels. Each channel can consist of covers multiple DIMMs, and within a DIMM you can have multiple ranks, and within a rank you can have multiple DRAM devices. And because, as I said previously, the banks are distributed across DRAM devices, so within the DRAM device you are going to have banks. Of course, here I've shown sub bank, but when you have multiple DRAM devices next to each other, one sub part of the bank will be available from one device, the next part is available from the next device, and so on, and you'll just combine all those things. That is going to be your DRAM bank. And each bank is organized as collection of DRAM arrays. So this is a logical organization of the DRAM memory. And now when we want to store some data into the memory, right? So now the commands we have to give such a way that it is going to say, okay, we have to store the data in this particular location. Though in a logical sense, we view memory as a collection of array locations and so on, and contiguous locations and so on, our data is going to be placed. But physically, they may be stored in different places. Even though you have two consecutive blocks, but they may be stored in completely two different devices, or two different banks, or two different ranks or channels. That all depends on how we are implementing the address mapping mechanism inside the DRAM memory. So, but before going to discuss this memory, the functionalities of memory controller, so let us spend some time on this particular organization part. If I just consider a DIMM consisting of two ranks, and each rank has 4 devices, and each device has 8 banks. Now, how this organization will look like? So this is what is going to be the thing. So my DIMM has 2 ranks. One side I have one rank, the other side I have another rank. And within a rank, you can see there are 4 devices, and within a device you have 8 sub-banks. In other words, my bank is now distributed across 4 devices. 1/4 of the bank is there in one device, another 1/4 is there in the second device, third 1/4 is there in the third device, and the last one is there in the 4th device. Whenever I want to read the data from, let us say, bank 0, so I need to send the signal to all these 4 devices, and then the bank will be activated, and from there a particular row I'll be activating and reading the data into sense amplifiers. From there, data will be sent to the data output buffer, and which in turn is going to send it to the memory controller. So if I want to access a particular row inside a DRAM, right? So here, for example, let us say this is a bank 0 of rank 0. So I send the command such a way that it is going to activate rank 0, and within that it is going to activate bank 0, and within that I'm going to select, let us say, row 0. And again, as I said, 1/4 of the row will be available from one device, and the other 1/4 is from the other device, and so on. So as a result, like a single command is given, and multiple devices are consecutively or simultaneously in working condition, and they will be supplying the data, which in turn reduces your overall time for retrieving the data. If you put everything into a single device, then it takes 4 times the original time, whatever we consider here. Because when we consider the data distributed across multiple devices, all devices are now acting in unison. When there is a request sent, and everyone is responding to that, and then each will supply 1/4 of the data. So your total time for transferring the data, right, the accessing the data, is now reduced to 1/4. And that is the main advantage with placing the data in this order rather than placing everything into a single DRAM device. So why do we need such an organization? Because we know that whatever the processor frequency and so on, right, ultimately the processor is going to work only if the data is available, and the processor always looks at the data in the memory, and memory performance is not that much improved over a period of time compared to the that of processor performance. So that is what is called as a memory wall problem. And to deal with the memory wall problem, we have this cache hierarchies and so on. But even if you have multiple levels of caches and so on, but you have to come to the memory to get the data, right? And but memory performance is not much improved. So to handle that situation, so these memory architects came up with these type of designs and so on, where some devices can work in parallel and some will be working in pipeline mode, but with the objective of improving the overall bandwidth, right? So supply more amount of data in a given amount of time. That is the main objective. So it provides bandwidth through pipelining requests or the parallel accesses. So you can send the request to 2 different ranks and so on in a pipeline fashion, or you can send the request to 2 different banks in a pipeline fashion and so on. And you can also send a request to multiple devices simultaneously and they can supply the data. You can see here the pipelining of request processing happens at the rank level and the bank level. I can supply one request to rank 0 and the next cycle I can send a request to rank 1. So both will be in a pipeline fashion, they will be operating. So your overall time will be reduced because the second rank is working in line with the first and so on. So most of the time will be overlapped, and at the end you will receive the double the data with a slight increase in access time compared to a single access from one particular device and so one particular rank and so on. And the same logic is applied at the bank level also. And the parallel accesses, as I said previously, if I want to access a particular row, I'll be sending the request to all these 4 devices simultaneously. Now all 4 devices are actually working simultaneously and supplying the data. And again, multiple DRAM arrays also again working at unison in the bank level. So within a bank, because a bank is distributed across multiple devices and so on, and so they'll also be supplying the data simultaneously and so on. Because you have the inherent the drawback of working the DRAM arrays working the lower frequency and so on, but because you have this parallelization and the pipelining concepts and so on, that actually reduces or overlaps most of the computation time and so on, and that reduces the average memory the time, so that you can supply the data to the processor maybe with 200 250 cycles and so on, because of all these optimization. Otherwise it would have been even more. And just not only this particular thing, but also there are many timing constraints the DIMM has to follow, and these timing constraints again provided by this memory controller. That means when I give a command, next command I cannot give without waiting for some X amount of time. So those things also will be provided. We'll discuss that in the coming slides. So what are the basic operations in DRAM? Because it's a dynamic random access memory. So every time whenever you want to read the data, so first thing what you have to do is you have to make this DRAM device or the DRAM array into a certain voltage level, proper voltage level, which is called as a pre-charge operation. So first you have to initiate the pre-charge operation, but once you initiate the pre-charge operation, it takes some amount of time to ensure that all the cells are at certain voltage levels and so bit lines, word lines and so on. Then you can give an ACT command. ACT command is nothing but, because you supply the data to the row decoder, and which is going to select a particular row, and now it is going to read the entire data from that particular selected row and return to the sense amplifier. That is what we are going to do with the ACT operation, activate operation. And once the data is, once we initiate an ACT command, again we have to wait for some amount of time, because the data has to travel from the selected row to the sense amplifiers, and it has to settle there in the sense amplifiers. After that, we can initiate a column access command saying that I want to read a particular block of data from this row which is sitting in the sense amplifiers. That is what is given by CAS, column access command. And this is going to read the data from the sense amplifier and then send it to the data out buffer, and which in turn is send it to the memory controller and so on. So basically, first we have to ensure that the DRAM array is in certain voltage level. Then we have to select a particular row and put it into the sense amplifier. Then we can read the data from the sense amplifier and then send it back. And if I want to perform a write operation, I'm not going to write directly into the DRAM array. Even if I want to perform a read or a write operation, What I have to do is first I have to read this entire row and put it to the sense amplifier. And any operation you want to perform, that should be on the data which is stored in the sense amplifier only. You cannot perform in-place operations in the DRAM memory. Everything should be done with the sense amplifiers. Even if it is a write operation, first read it into a sense amplifier and perform a write in the sense amplifier. And after that, you write it back to the DRAM array. So these are the three commands we have to give for accessing the data: pre, act, and cache. And also another thing is, as I mentioned previously, DRAM is a dynamic random access memory. And the data stored in the DRAM cell is in terms of the charge in the capacitor. And the charge in the capacitor is gradually leaking because the capacitor loses its charge over a period of time. So unless you refresh that, the data is not going to be maintained. For example, initially you wanted to store logic 1 and then you charge the capacitor accordingly. But over a period of time, because the capacitor is leaking, and after some time, if you want to read the data, the charge may be below the threshold, and then it can wrongly say that it is logic 0, but that is wrong. So you need to regularly refresh these DRAM cells. That is the reason why it's called the dynamic random access memory. Regularly, you have to just keep on refreshing to maintain the original data as it is. And that needs to be done. That is another important operation. So to retain the data, we are going to perform a refresh operation at regular intervals. And this refresh operation, refresh rate, depends on the temperature on the DIMM. If the temperature rises above 85 degrees centigrade, the capacitors are going to leak much faster rate. So that means it retains the data for a shorter duration, only 32 milliseconds. Otherwise, if it is up to 85 degrees centigrade, the data, once it is refreshed, it is going to be there for 64 milliseconds. That means within 64 milliseconds, I have to refresh once again. That means every 64 milliseconds, I need to refresh a DRAM cells, otherwise the data is going to be lost. But this is not just only refresh operation, there is also another operation called as a restore. Because as I said previously, whether it is a read operation or a write operation, first I have to read from the DRAM array and put it into the sense amplifier. Once I put the data into sense amplifier, that means once I read something from the DRAM array, the corresponding cells lost its data. Now you have to restore it back. That is what the restore operation. Every read you perform in the DRAM array, you have to restore it back. That is irrespective of whether you have done refresh or whatever. If you read something, then you have to do that. And a refresh is also exactly same as the restore, because a refresh is nothing but read the data into sense amplifier and write it back into the DRAM array. So all these operations you have to do every time. And this is also again adding extra latency to the overall DRAM operations and so on. And if you see some of these latest DRAM DIMMs, which have a capacity up to 32 GB or something, in such high density DRAM devices, your refresh operations are actually occupying almost 35%, 25 to 35% of the total time. That means during the time when the refresh is happening, CPU side, if there is any request to that particular bank under refresh, that request cannot be serviced because refresh is having the higher priority. Once you are doing something refresh, any request from processor side will be stalled. So once it is stalled, then automatically processor side, it will see a significant performance degradation and so on. That is where like people propose multiple options, multiple optimization techniques to reduce the overheads associated with this refresh and so on. Or some people also looking at why can't we replace the DRAM completely and then coming up with new memory technologies. For example, emerging memory technology, phase change memory, STT-RAMs and so on. These are different technologies people are coming up with. And there are some processors which are actually using STT-RAM based RPCM based memories, but they're not completely replacing the DRAM as such, but they are considering DRAM and some part of the memory using this emerging memories and so on, where you don't need any of these overheads associated with the refresh. But the technologies are not matured enough, so their endurance is very limited. That means you cannot use that for many number of writes and so on. So typically you have like after some millions of writes, the device is going to cease to work. So there are some other issues and so on. But so for the emerging memories to mature, It takes at least maybe another 5 to 10 years and so on. But till the time this DRAM memory is going to be there.
So,
yeah, go ahead.
Sir, could you again explain that point? DRAM reads are self-destructive.
Yeah. So DRAM read is self-destructive. Is like, because maybe I'll just go back to the example. Yeah. Right. So here, I want to read the data from a particular row. Right. So what is that I'm going to do? I'll just go back here. Yeah. So when I want to read from a particular row, I'm going to read the data and put it in the sense amplifier. How do I read the data from a cell? I'm activating the bit word line, I'm activating the bit line, and then I activate this access transistor. Through that, I'm going to read the charge in the capacitor, and which is going to be sent to sense amplifier, and sense amplifier is going to sense that, and accordingly it amplifies the signal, say whether it is logic 0 or logic 1. But once you do all these things, now the charge in the capacitor is completely drained because you already read that. Unless you store the actual value into the capacitor, next time if you want to come back to this DRAM cell, it is not going to give anything, right? And because you already read the entire charge in the capacitor, now you have to restore the charge back. How do I restore? Once I send the data to a sense amplifier, then sense amplifier says that, okay, this is logic 0 or logic 1. And then I'll be again writing appropriate charge into the capacitor. That is what is the restore operation. You have to do that. Otherwise, the cell is not going to have any charge, and the data next time if you come to the DRAM cell, nothing will be there in that. Or it gives a wrong information. If it is a true cell, and it can give you, if it is a logic 1 initially stored, and it can give you logic 0 because the charge is completely drained. Or if it is an anti-cell, if the logic 0 is there, next time it is going to say logic 1 and so on. So you need to fill the capacitor with the charge, original charge. And that will be done by, from the sense amplifier, I'm again writing back to the corresponding DRAM cell. That is what the restore operation.
Okay, all right, so thank you.
Right. So as I said previously, the DRAM DIMM is a passive device. It cannot do anything on its own. So there should be a controller which is going to say what needs to be done. And like any other, for example, cache, you have a cache controller and so on. Similarly, memory also, you have a memory controller. And this is what is the memory controller typically. You have processor and IO and so on that are connected to the memory controller, and memory controller in turn connected to the DIMMs. Basically, the memory controller is acting like an interface between processor IO and the DIMMs. And processor, when it sends a request, maybe a read from a particular location or write to a particular location or whatever. So those requests will be sent to the corresponding queues, a read queue and a write queue. And there is a request scheduler which is going to select a request either from a read queue or a write queue. And that request will be converted into memory understandable commands. Because processor says, LLC, when there is a miss, it says, okay, load the data from this address. But DIMM cannot understand anything. For that, what we have to do is, we have to convert this load request into commands like, okay, so read the data from this particular location. That is nothing but you first pre-charge this particular location, activate this particular row, and then read column from that particular row. That is what we have to give. That means this load command is now converted into pre-act and cache. And that will be like this command conversion, request to a command conversion. And we put it into appropriate queues here, command queues. And then there is a command scheduler which is going to pick one of these command queues. And from there it is going to read the data, or the commands. And that command will be sent to the DIMM. And DIMM is going to now act on that command, and it supplies the data bit by bit. So it cannot supply 64 bytes of data in one go. Maybe 64 bits of data every time it will be transferred. And that will be sent to the response queue. And from the response queue, memory controller sends the data back to the processor. That is what is going to happen whenever there is a LLC miss, for example, and which consists of all these operations in addition to your refresh operations and so on. What are the main functionalities of this DRAM memory controller? First, as I said previously, memory requests will be converted into DRAM understandable commands, pre-act and cache type of things. And also it enforces the timing constraints. Once I give a pre-command, I should not give my act command within next so many number of cycles. And when I give an act command, I should not give a cache command within next so many cycles. And if there is a refresh operation, I should not service any other request until this particular time is completed. All these things will be there. That is what is part of the timing constraints. And when we read the data from a selected row and we are going to put it into the sense amplifier, this is also called as, from the DRAM terminology, it is also called as a page, DRAM page, which is typically 4 KB of size, or we also call it as a row buffer. The sense amplifier thing is called as a row buffer, where DRAM row is going to be stored. And every time, only for per bank, only one row, a DRAM row buffer will be there, which is going to store only one row of data. But now, when we place the data in the sense amplifier, how long we can keep the data in the sense amplifier? Can I keep that forever? Or once I request a service, can I just write it back to the memory? What is that we have to do? That is what is given by this row management, row buffer management policies. The next is address mapping. When I have consecutive blocks, where do I store these consecutive blocks? Is it going to be there in the single bank, or is it going to be there in different banks, or is it going to be there in different channels, or whatever? That is what is specified by this address mapping. And this also, again, another crucial component which is going to actually determine the overall effective performance of this memory. And as I mentioned previously, every regular intervals we have to refresh the DRAM cells, otherwise the data will be lost. And that is what is handled by refresh management methods. And finally, we have schedulers which are going to select the request from the read queue, write queue, and similarly command queues. That is what is memory scheduling. These are the 6 major functions provided by a DRAM memory controller. By the way, so the memory controllers these days in the modern processors are there on the chip, so that the memory controller can work with the processor frequency. That is the main advantage on chip DRAM memory controllers. But how this memory controller is designed in real processor, AMD processors, Intel processor, IBM processors, and so on. So no one is going to reveal those details because these are like their IP. But whatever we are discussing is generally any memory controller should have these properties and so on. We will be discussing this at an abstract level, but the actual implementation may vary processor to processor and so on, depending on what they foresee and what type of benefits they are going to get with one particular design over the other, and accordingly they are going to decide their memory controller designs and so on, and that none of the processor vendors is going to reveal those details and so on. So whatever the material I'm covering is actually from a book, a standard book called as a Memory Systems by Bruce Jacob, and you can find this material there, and it's like a, I think, 600-page book which consists of DRAM memory, caches, hard disk, everything they have discussed in detail and so on. But whatever the memory controller we design, the overall objective is to maximize the system performance and minimize the power consumption. With these goals, typically different memory controllers are designed by different vendors and so on. Of course, when they decide this memory controller, they'll also see underlying the DIMMs and so on, what DIMMs this particular memory controller is going to operate and so on, because the DIMMs are going to be designed based on JEDEC standard, which is like a consortium which talks about, which defines the standards for the DIMMs. Right now, we will be using DDR4 DRAM devices. Previously, DDR3 is there, DDR3 low power, DDR2 and so on, and even DDR5 is also there. You can go to JEDEC website, jedec.org. There you can find all this information about new standards for the DRAM memories, or the previous versions and so on. And similarly, for GPUs, they consider GDDR technologies, GDDR standard. So there are different designs are there, and different standards are defined for each of these, the memory components and so on. The first one is converting memory requests into memory commands. That means a load or a store converted into pre, act, and cache. So we'll discuss that with an example here. So memory requests are load and store, and memory commands are pre, act, and cache. Let us say we have these 4 requests. One is load the data from row 0 and column 4. That means the column 4 of a row 0. Second one is load the data from column 5 of row 0. Third request is read from column 1 of row 1. Fourth is store the data into column 3 of row 1. Let us assume that all these 4 requests are going to same bank. Now, if I schedule these requests in the same order, how many commands I have to give? How many memory commands I have to give? If I rearrange these commands, how many memory commands I have to give? That is what we will discuss. and assume that once I open some row and put it into a sense amplifier, the sense amplifier is going to maintain the data unless until if there is a conflicting request come to that particular one. That means if I open a row 0 and I'll keep the data in the sense amplifier until unless there is a request for any row other than row 0. The advantage with this is if you are getting subsequent requests to the same row, you don't have to access the DRAM memory because everything is there in the sense amplifier, and from there you can supply the data to the processor. So that is effectively, it is going to get a hit in the row buffer, and if you increase the row buffer hit rate, it is going to improve the overall performance. So this is called as an open page policy. Once we open a page, we keep the data in the sense amplifier unless until there is a conflicting request. That is what is called as open page policy. Let us assume that we are considering open page policy. Now we'll see for this particular one, if these 4 requests are there, how many commands we are going to issue. Now you can see the first command, we have to initiate a pre so that the bank will be in a certain voltage level. Then we issue an ACT command to row 0. So the row 0 data is going to be read into sense amplifier. Once the data is available in sense amplifier, we'll issue a cache command so that we'll read the data from column 4. Now the data is there in the sense amplifier. Now the next request, again to the same row. So I don't need to go to the DRAM memory. So as a result, I don't have to perform pre and ACT, because the next request is also from the same row, which is already there in the sense amplifier. All I have to do is give only a cache command. But the third request, it is to a different row. Once it is to a different row, now there is a conflict at the sense amplifier level. So I have to close this page, which is there in the sense amplifier, and then set this entire DRAM array into a certain voltage level. So for that, I'm going to give a pre command, then read the data from row 1. That is what I'm giving ACT command. And then once the data is available in the sense amplifier, I'm going to give a cache command to read the data from column 1. Next, a store operation to the same row. So again, I don't need to perform pre and ACT, but I have to perform a cache command. So basically, now if you see a total of 8 commands you have to give for this 4 memory requests if we use this particular policy. Got it? Right? So now if I consider a slightly different request order rather than R1, R2, R3, R4, if I consider a different order, we'll see what is going to happen. Okay. So if we consider a different order, R1, R2, R4, R3, that means the last 2 requests we rearranged, because all these requests are there in the read queue, write queue. Then I can just reorder and then I can issue these requests to the DIM. So now I consider R1 first, R2 second, then R4 and then R3. Here also, interestingly, the same number of memory commands I have to give, like the previous reorder. But it actually incurs extra latency because we have write to read latency. Where is this coming? Why this write to read latency is there in this particular one, but not there in the previous one? Any idea? This is because so actually what is happening is, like, because the DRAM DIM, it is servicing both the read and write operations, and there are some circuitry which is actually used for both operations. If you are performing a write operation and if you want to perform a read operation, you have to wait for some amount of time so that this output circuitry will be settled and then it's ready to process the read request and so on. So for that, we have to wait for this read to latency for store to load or write to read latency and so on. WTR, we typically call it as. And this latency is typically few cycles. 2 to 4 cycles will be there, and you have to wait for those many cycles so that your output circuitry is going to be settled, and then it is going to perform the operation for read operation. But that is not there earlier, because if you see, the store is the last operation in the previous order, but here store is the third operation. After that, there is a load operation. And if I consider something else, R1, R4, R2, R3, which is a bad reorganization, if you see in all this, you're not exploiting the row buffer locality. You first open row 0, next row 1, next row 0, next row 1. So as a result, you're always going to close it and so on, which is going to incur 12 memory commands compared to 8 memory commands and so on. So this actually says that once you convert this request, right? So if you want to exploit this row buffer locality and so on, you have to intelligently select your memory request. That means a scheduler selecting a request is also plays a big role here, which is going to utilize the command entries efficiently, because you have limited number of entries in each command queue, right? And you have to utilize that efficiently. So that means if you can exploit the locality, then you can reduce the number of operations. And so as a result, your DIM also will be supplying the data quickly. And to do that, we have to see which requests can be combined together and then are scheduled one after another so that locality can be exploited.
Sir,
Yeah.
I have a doubt in the previous slide.
Yeah.
Like when we have the two columns same, so we can use the cas command similarly, like we use the act command in the exploit page access locality case and right, sir?
Yeah, so if you're going to exploit the page locality, so basically we are just giving only one time act command and then the data is stored in the sense amplifier. After that, you'll have multiple cas commands. Yes.
Okay. Definitely.
Right?
Yes, sir. Understood.
Yeah. So when you are exploiting the row buffer locality, effectively you are giving multiple cas commands and a single act command. Yeah. So if we just see, because we have converted the memory requests into memory commands. Okay. So now we'll see how this is actually, this entire processing happens inside the DRAM array. Right. So I said when there is a load request, we give an address. So the address will go to this address register. From there, half the address will be sent to the row buffer, the row decoder. Other half will go to the column decoder. And row decoder is going to select a particular row, and that will be sent to the sense amplifiers. And then the column decoder is going to select a particular lines from the sense amplifier array, and that will be sent to this IO gating, and which will be sent to data out register, and which in turn writes to data IO, and from there it will be sent to the processor side or the memory controller side. And if it is an store operation, some data is coming from the memory controller, and which will be sent to the data IO, and which in turn sent to data in register. From there it will come to the IO gating, and then it will be returned to the sense amplifiers location specified by this row decoder positions and so on. Okay. So that is what is going to happen. Now if you see the third and fourth operations, right? So when you have this write operation and the read operation, this circuitry is common. So you need to wait for some amount of time so that this IO gating circuitry, which earlier processing the write request, now will be settled for processing a read operation and so on. That is where we have TWTR, time for write to read latency, whatever we considered in the previous slide. And this is what is going to happen. And when there is a request, and the request, whether it is a read or a store operation, now we'll have a corresponding commands, we'll convert into corresponding commands, and the commands are going to be there in the command queue. And from there, we'll decode that, and then we'll perform the operations. And also we said like the refresh operation will be there. So that is also, there is a refresh counter, which is going to send the row address, and that particular row will be read and then performed. This is what is going to happen inside when there is a request sent from the DRAM LLC to the memory controller, and memory controller will send all these things, and finally it will reach the DRAM array, and the DRAM array is going to supply the data. And this is what the reference I was talking about. Memory systems, cache, DRAM, and disk by Bruce Jacob and team. There are plenty of timing parameters DRAM DIM is going to consider, but I'm not going to talk about all those things. Those who are interested can look at the textbook for full details, but I'm going to focus on some important timing parameters, and at the end I'm going to show what are the typical values for each of these timing parameters. So we said previously, we give a pre command and then we give an act command. But how long I have to wait for issuing an act command after pre is issued? That is what is determined by TRP, row pre-charge delay. That means once you pre-charge a particular row, you have to wait for TRP amount of time to issue an act command. So that now the data is read from this particular the row and put it into the sense amplifier. And now if I want to read a cache command, right? how much time it is going to take. So those things also there. So for example, row to column delay, which is nothing but once I give an ACT command, at what time the data is going to be available in the sense amplifiers. That is what is TRCD, row to column. From the DRAM row, it will be sent to the sense amplifier. And then so that you can perform your CAS command or whatever. And for that, you have to wait for TRCD amount of time. And if I issue a pre-command, right? So if I issue an ACT command to read the data from a selected row, at what time I can give a pre-command so that I can open on, let us say I opened row 1 and now I want to open row 0. How much time I have to wait? That means before opening row 0, I have to perform a pre-charge operation. That is what we consider the previous example. When there is a row conflict, I'll be performing a pre. But at what time I can give a pre? That is determined by this TRAS. Okay, which actually says TRAS is equal to TRCD plus data restoration. Because when you perform a TRCD, which is nothing but read the data from a selected row and put it to the sense amplifier. Once you put the data into a sense amplifier, your original position in the DRAM array lost the data. Now you need to restore the data. That means from the sense amplifier, again, you have to write it back to the DRAM array. That is what is the second component, data restoration time. So you need to wait for data restoration time. Only then you can actually go for the pre-command and so on. And once the data is there in the sense amplifier, I want to read column by column. Let us say I want to read column 0 data, next column 1 and so on. But for reading the column 1 data, after the data is available in the sense amplifier, I have to actually wait for TCL amount of time. That is effectively once I give a CAS command, it is going to take TCL amount of time to get the data on the bus. So the time interval between the column access command and the start of the data written by the DRAM device is a TCL. And when I read the data from column 0, now if I want to read the data from column 1, even though it's the next column in the same row, but I have to wait for some amount of time. That is what is called as CCD, column to column delay. Even if you are reading from the same row which is there in the sense amplifier, you have to wait for TCCD amount of time, because once you are reading the data from a column, it is not just going to take one cycle, because you read the data in cache line granulate, which is typically 64 bytes, but this will be transferred in bit by bit, and that takes multiple cycles, and you have to wait for those many cycles. Then you can start reading from the next column or whatever. And the amount of time the data occupied in the bus is the TBL. And there are many other things also. For example, you can see here, write to read delay I mentioned previously, right? The time for the IO getting resources to be released by the column write. Previously we are performing write, now we want to perform a read operation. Now we have to release those IO circuitry, which takes TWTR. And if I access a row 0 now and I want to access a row 1 data, how much time I have to wait? So that is what is given by row cycle time, TRC. That means row pre-charge plus TRAS. These two times you have to wait. And that is the sum of the times you have to wait for performing operation from a different row or activating a different row in the same bank. And a refresh, as I mentioned previously, regularly we have to refresh. And once we issue a refresh command, the next ACT command can be given only after waiting for TRFC amount of time. And let us say your DIM has 2 ranks. You are currently operating with the rank 0. Now you want to operate the data from rank 1. That means you want to read the data from rank 1. Then one rank to another rank you have to switch. And that also takes some amount of time, a couple of cycles and so on. But if you put all these things into perspective with the latest technologies, for example, DDR4 DRAM, that is what mostly all our laptops or desktops have, or otherwise DDR3 low power mode, DDR3L. If you see the values, right? So for example, TRC, if I want to read from different rows of a same bank, I have to wait for 39 DRAM cycles. And if I'm issuing a refresh command, so next 280 cycles, the device is not available for servicing any request from the processor, that particular device. And similarly, if I want to read data from multiple columns of the same row, I have to wait for 4 cycles. And if I move from write to read, then I have to wait for 6 cycles. So that's the reason why it's also another motivating factor for us to keep servicing the request from reads continuously, and then move to writes, and then perform writes continuously, and then move back to reads and so on, so that you can amortize this cost. Otherwise, like if you're scheduling in a very bad way, that first read, next write, read, write, read, write, and every time you are going to incur extra 6 cycles and so on. That's not a good idea. And once you give a column command, cast command, it takes 11 cycles to get the data appeared on the bus. Right? All these are like different parameters, and because of these things, if you see when there is a miss in the last level cache, we'll be typically taking hundreds of cycles to get the data from 150 to 200, 250 cycles to get the data from DRAM memory and so on. And so as a result, like there are several optimizations people proposed and so on, but internally the memory is going to operate like this with there's so many timing constraints and so on. And then I mentioned the row buffer management policies, right? So the row data is read into sense amplifier, and which is also called as a row buffer. And how do we manage this row buffer? A simple technique is we can consider open page row buffer policy. That means once the data is there in the row buffer, you keep it there unless until there is a conflict. Only if there is a conflict, then you close this page and then open the new page. The advantage is if your application is executing more row buffer locality, that means you are keep on reading from the consecutive locations in the same row, then all you need is like you incur only TCL amount of latency. Because if there is a hit in the row buffer, you don't have to perform row precharge, row RCD and so on, RCD latency and so on. You just have only TCL latency. But if your application is not exhibiting row buffer locality and reading from different locations and so on, the open page policy may not be a good idea. For example, if you are considering the memory in data centers and so on, where requests coming from different applications and so on, they may not exhibit any locality. In such cases, maybe this policy may not be a good idea. We have to consider something else. So on a hit, open page policy is going to take very less amount of time, but on a miss, it is going to take full latency, TRP plus TRCD plus TCL. So if I consider the other policy, because I open the row for servicing one request, once the request is serviced, I just close it. So that the next request when it comes, the sense amplifier buffer is empty and you already made the buffer, the DRAM bank precharging is already done. So you don't incur TRP latency in the critical path. So always your latency will be TRCD plus TCL. Here the assumption is your request will be coming once in a while with a gap, right? If that is the case, once in a while, if you are getting a request, that means a low access rate, the rates are there for applications, then in that case, the closed page policy is a better thing. You can close the page, the TRP is not in the critical path. And so effectively, whether it is a hit or a miss, because there is no concept of hit here, because you service one request and close it. Next time when there's a request, again, you bring that by issuing an add command and then the cast command. So your latency will TRCD plus TCL. Compared to a TCL versus and TRP plus TRCD plus TCL. So that means depending on the application characteristics, either we can go for open page policy or closed page policy, or we can also go for something else intermediate to these two. That is called as a hybrid policy. We can set some time for this row to be open. When the page is open, when the data is stored in the sense amplifier, we'll keep that for some amount of time. Within that time period, if there is another request to the same row, then again we extend the time. If there is no request, then after this time elapsed, then we'll just close it. That is what is called as a hybrid policy. So precharge command is issued when the timer reaches 0. Once the timer reaches 0, then we'll just write it back to the memory and then issue a precharge command and so on. But otherwise, it will be there. And this is generally better where applications have this access rates and the request rates are dynamically changed, because you can set this timer accordingly and by looking at the application characteristics and so on. But this is an intermediate to open page and the closed page policy. Now, if we consider these three with an example, let us say we have 4 requests and these requests are coming at different times. At time 0, we have a request to column 4 and row 0. At time 40, we have a request to column 5 and row 0, same row. And at time 70, we have a request for column 3 and row 1. And at 140, request from column 1 and row 2. And initially, the precharge is already done. Now, the sense amplifier is empty. Now, when there is a request at cycle 0, now in the open page policy, what I'm going to do is I'll issue an act and cast command and bring the row 0 page into sense amplifier. Next, because the open page policy, the data is there in the sense amplifier. Next request at 40, which is also to the same row. So you'll be lucky. You can service with just only cast latency. And then again, the data is still there because it's open page policy. But at 70, we have a request to another row. So we have to close this and then perform a pre-act and so on. So we incur pre-act cast latency. And again, this same row is going to be there, but at 140, there is a request for another row. Again, we are going to incur pre-act and cache in the open page policy. But in the case of closed page policy, first one empty, so we perform act and cache. Immediately after cache is performed, then I'm just performing a pre-command because I'm closing the page and making the pre, so that at 40, when the next request comes, again, we'll be performing act and cache only, and only the other two also. But in the case of hybrid, if you see, we set the time as 50. And at cycle 0, we brought row 0 page and put it into the sense amplifier by giving act command. Now this data is going to be available for the next 50 cycles. That is what the threshold we gave, right? 50 timer. But at 40 itself, we received a request for the same row. That means now I'm going to reset the counter back to 50 again. That means this row is going to be there for the next 50 cycles. That means from 40 to another 50, that means up to 90, cycle 90, it is going to be there in the row. But at 70, there is a request for a different row. So now I'm going to incur pre also there because I have to close this and then open the other. At 70, I opened row 1. 70 to 50, that is 120, up to 120, the row is going to be there. But at 140, I received another request. That means by the time already I closed this page. And now for 140, actually there is a typo, which is actually act plus cache should be there. I just put only cache, but this is last one is act plus cache. So that way, like you can compare to open page policy, you can slightly get the benefit because there are some requests which are coming once in a while, and you can close the open page and then you'll not incur pre in the critical path and so on. But the current memory controllers, they're coming up with some techniques similar to this, but they will not disclose all these details and so on. But because this is one of the crucial things which is going to determine the effective access latency from the memory. And so that's the reason why they put much attention here in addition to the address mapping part and so on.
So,
yeah.
So can you go to the previous slide?
Right, yeah.
So in this table, so we have a page status as hit for row 0 and column 5. So so that is understandable if you are basically following the open page row buffer policy. Because
yeah, so this empty, hit, miss, these are only for effectively the open page policy, you can say.
Okay.
Right. But in the hybrid also, so basically what we are saying is like, let us say these are the requests and the hit, if you say this request is same as the previous request to the same row, then we say row hit.
Okay.
Right. Because let us say if you see first two requests to the same row 0, then we say it's a row hit. It's not at the entire row we have a hit because the data is there in the sense amplifier. That's it.
Okay.
Yeah. But this row hit will come into picture only when you use open page policy and hybrid policy. Hybrid policy also, if the data is there in the sense amplifier, during that time you can exploit this hit. Otherwise, like you have to close it and then.
Okay, sir.
Yeah.
And just one more thing. So like you talked about like this row buffer locality. So so is it like I might be like going a little ahead. So like is it like possible that we can expose this row buffer locality to the programmer so that he writes the code such that he
No. So because we don't know how the data is going to be laid out. And also another thing is like when you are executing a program, you may be executing on different computers, right? And you don't know what type of memory control design is there. And memory control is going to determine where the data is going to be placed. Which row, which bank, which rank, channel, right? So, but if you do some reverse engineering on the current processors with the memory controller, reverse engineering memory controller, and if you know that, then probably you can use that information.
Okay.
But you cannot give a strict rule saying that, okay, the data is going to be, you cannot force the memory controller to place the data in this particular location or whatever, and then I want to exploit the locality, right?
So since the memory controller is responsible for basically spreading out the data in the DRAM. So is it the memory controller only which does this address space randomization?
Yes. Yeah. So again, there are techniques. For example, there are mechanisms for reverse engineering the DRAM memory controller, and to see what is actually implemented in Intel-based systems or AMD-based systems and so on. For example, there is one recent paper on attacks on DRAM-based memory and so on. There they actually looked at, I think, yeah, in Intel-based systems. I think Rowhammer-related stuff, for example, you can come up with the attacks on the DRAM rows and so on. But there they looked at like reverse engineering the memory controller and so on. But it takes good amount of effort to see what is actually implemented inside. But yeah, if you get that, then probably you can do something. But this memory and so on, typically these are like completely transparent to the programmer. OS also will view this entire memory as a logical sequence of error locations and so on. It will not know anything about rank, channel, bank, and so on.
Okay, sir.
Right, yeah. So address mapping is another crucial component in the memory controller's functionality, which is actually going to say where the data is going to be placed. And the objective of any address mapping, good address mapping technique, is to reduce the conflicts at the bank level, right? So if you are going to have the data, consecutive data, if you are going to keep accessing, it is better, let us say you are trying to read the data from 2 consecutive cache blocks. It is better you place these consecutive cache blocks into 2 different channels so that these 2 channels can simultaneously work, and then you'll get the data, 2 blocks of data in 1 unit of amount of time, rather than placing these 2 into the same bank, or to 2 different rows in a same bank. If that is the case, then first you have to close it and then open the other one and so on. So you need to ensure that this address mapping technique is going to improve your parallelization and reduces unnecessary conflicts. That way, like, you can extract more performance. But for that, we have to see what are the places where we have parallelism available inside. So there are different granularities parallelism available in the DRAM. The channels is the highest level of parallelism. 2 different channels are independently working, and you can distribute your data, your interleave your data across these 2 channels. First block here, second block here, third block in the first channel, second block in the second. So if you just reorder, if you interleave like that, so 2 channels can simultaneously work, and that can give you a good the rate of data transfer and so on. And the ranks, it is better you put the data into the same rank rather than distributing across multiple ranks inside DIMM. If you put that, because rank to rank switching of 6 DRAM cycles going to take place. So the rank to rank switching penalties will be there, and you need to try to minimize that. And the banks, again, you can have multiple banks inside a rank. You can supply the data to different banks, but of course they can be performed in a pipeline fashion. Okay, so consecutive requests can be sent to different banks and within a rank, and they will be operated in a pipeline fashion, because ultimately when you want to send the data from the DIMM to the memory controller, you have some shared resources, and that will be shared across multiple banks. At any point in time, only one bank can use. So that is where this pipelining coming into picture. One after another, they can transfer the data. And the rows within a DRAM array, only one row per bank is always active, right? And if you distribute your data to multiple rows in a single DRAM bank, and if you try to read that consecutive ones, then you will always incur row conflicts, and that degrades the performance. And columns, which are like typically we consider cache line size, and so better we map this column address to the lower address bits if you are using an open page policy, and higher address bits if you are using a closed page policy. Open page policy is nothing but we open the row until there is a conflict. In such cases, if we keep the column bits to the lower order bits, because the lower order bits, what happens is like the activity will be much higher in any address. If you consider in any n bit address, the lower order bits have more activity, change of bits. The rate of change of bits will be higher at the lower order bits compared to the higher order bits. So once it is changing, and if we map those bits to the column, so we may be reading consecutive columns and so on, but they are mapped to the same row, then we can exploit the row buffer locality if it is an open page policy. But if it's a closed page policy, every time we have to close it and then open, right? In such case, it's better you move the column bits to the higher order position so that there's a less activity, and so you will not incur the pre in the critical path and so on. And given this, of course, I'm not going to go through this part. It's like the total size of the memory we can consider as K into L into B into all. So which are like effectively the size of the channel, number of channels, number of ranks per channel, number of banks per rank, number of rows per bank, number of columns per row, and the number of bytes per column, and put together all these things is going to determine your total size of the DIMM. And with that, we are just considering what is the baseline open page policy. Open page policy is nothing but a page is stored in the sense amplifier and it will be there unless until there is a conflict. If we consider open page policy, what type of addressing mechanism we have to give? And it will be roughly like this. R, first higher order bit should be part of R, next L, next B, N, K, Z. Z is corresponding to cache line. The number of bytes per cache line, that is the offset within a block, that is part of this Z. And K is effectively your channels also to the lower order bit positions. N is your number of cache lines per row. How many? Because if you consider a 4 KB page on 64 bytes of block, so in a 4 KB there are like how many? So 64 means like 64 blocks can be stored in a single row, and 64 is basically 6 bits, and that 6 bits are going to be specified using this N. And similarly, number of banks per rank, the next couple of bits, and after that L, which is the number of ranks per channel, and finally number of rows per bank. So the rows per bank we put at the MSB side. Mainly higher order bits are mapped to the rows per bank because it's an open page policy. We try to minimize accessing multiple rows from the same bank. How do we do that? We move that to the higher order positions, so the bit activity will be less in that. So as a result, there's a less chance that we will be reading from consecutive rows of the same bank. And that is the idea we consider R towards the MSB. But whereas Z is towards the LSB, because there will be multiple bit transitions happen, and effectively, which is going to say we'll be reading the data from multiple columns and so on, and which are mapped to the same row, because there are 64 consecutive blocks can be mapped to the same row, and you can exploit the row for locality. And if I consider this with an example where, let us say I have 2 channels and 2 ranks per channel, 2 banks per rank, 1 row per bank, and 4 cache lines within a row. Now, how do we map these cache blocks onto this 2 channel DIMM, with each channel having 2 ranks and each rank having 2 banks, and each bank having 1 row, and 1 row has 4 cache blocks. So if you see, block 0 is stored in channel 0, rank 0, bank 0. And the next consecutive block, which is block 1, where did I put? I put it in channel 1, rank 0, and bank 0. That means now if you see, if you want to read from 2 cache blocks 0 and 1, these 2 requests simultaneously sent to 2 channels C0 and C1, and both will be supplying the data in unit amount of time. Now after that, let us say the next block, that is block 2, where do I put? Because it's an open page policy, I want to try to put the data into the same bank and the same row and the same rank, because I don't want to incur rank to rank switching. So that's the reason why if you see, block 2 is placed in the same channel, channel 0, same rank, rank 0, and bank 0. Similarly, the next block, which is block 3, I placed in the other channel, channel 1, rank 0, and bank 0. Right? Because 1 row can accommodate 4 lines. So now the next 2 also, for example, 4 and 6 also to the same bank, same rank, and same channel. And similarly here the other channel, 5 and 7 also. So basically, block 0, block 2, block 4, block 6, all these 4 consecutive 4 blocks are placed in a single bank of same rank of channel 0, and the other 4, 1, 3, 5, 7 are placed in the bank 0, rank 0 of channel 1. So effectively, I'm exploiting the parallelization at the channel level, and I'm exploiting the row buffer locality because I put all these things into the same row when I access a particular bank, and then I'm going to get the benefit because it exploits the row buffer locality. But this is useful only if you're using open page policy. But if you're using a closed page policy, the moment you open a row, you are going to close it after passing the request. Next time, if there is a request to even the adjacent block or to the same block, again, you have to perform a pre and act and so on. So in such cases, it is better adjacent blocks are not going to be placed in the same row. And that is what is done in the case of closed page policy address mapping. Again, we'll just consider this block 0 to block 7. Now, if you see block 0, I put it in channel 0, rows rank 0 and bank 0. And block 1, fine, I just put it in channel 1, rank 0 and bank 0. But block 2, previously in the open page policy based address mapping, we put it into bank 0, but here we put it into bank 1. Why? Because if I have a request for 0, 1, 2 blocks, 0 went to channel 0, 1 went to channel 1, fine. But if 2, in the case of closed page policy, because I maybe started processing the request for block 2, but previous request is already done and now it is slowly closing. When it is closing, then the pre is coming to picture. So I don't want to incur that penalty. So as a result, my next request is actually, next block is stored in bank 1. So that while closing operation is happening on bank 0, opening operation is happening on bank 1 in a pipeline fashion. So you will not incur the pre happening in bank 0 on bank 1's operation. So that is the reason why we place block 2 into the other bank compared to the open page policy. And similarly, 3 also we put it into bank 1 of channel 1 and rank 0. And then the next 4, where do we put that? So 4 is again, we put it into the channel 0, but different rank. Because rank to rank switching is actually taking less amount of time compared to issuing a pre-charge operation. So you need to see the trade-off, because a pre-charge operation may be taking 11 cycles or 12 cycles, but whereas a rank to rank switching may be taking like 6 cycles. So you can save that. That's the reason why we just came here to rank 1 of channel 0 and put this block 4 in bank 0. And similarly, the other things carry forward. So these are basically, once we fix this address mapping, once we fix the row buffer management policy, then we can see the suitable address mapping mechanism, so that when these two are working together, now you can get a better performance and so on, depending on your application characteristics. And then the last 2 functionalities, one is the refresh management, the other one is the scheduling part. Refresh, as I already mentioned, so we need to refresh regularly, otherwise the data is going to be lost. And how do we do that? We already saw RFC, TRFC is 280 cycles. But if you are going for the 280 cycle refresh, if there is any request from the processor side to that particular memory, that particular bank, the bank is not going to service the request, because the refresh is having the highest priority. And if you consider a multi-core system with 28 or 32 cores and everyone is requesting the data from a DRAM memory, and if it says, oh no, I'm just doing refresh operation, I can't service any request, then user side will see a significant delay. The performance is going to be degraded. That is where there are multiple options proposed on efficient refresh managements. And one such method is typically distributed refresh. And JEDEC actually specifies that any memory controller issues 8K refresh commands. That too in every 64 milliseconds. Every 64 milliseconds, we have to give 8K refresh commands. And these 8K refresh commands is independent of what is the size of the memory. You may have 4 GB memory or 32 GB memory or whatever. But for all the things, you have to give the same number of commands. So it means if you have a high density DRAM memory, with one single refresh command, you have to refresh multiple rows. If it is a low density DRAM, with one refresh command, you may be refreshing only one row. But as I said previously, refresh is nothing but read the data from a row, put it into the sense amplifier and write it back to the DRAM array. And if you are refreshing multiple rows for a single request, let us say for one request, you are going to refresh 8 rows. So 8 rows, one after another, you have to read it to a sense amplifier and write it back. If you increase the number of rows, then it is going to take good amount of time for every refresh operation. And in the case of distributed refresh, what they have done is they divided the 64 milliseconds into equal granularities, the intervals, and each interval they are going to issue one command, because there are like 8K refresh commands, right? One refresh command they'll issue, they wait for some time. In this time, they'll service the processor request, and again they'll issue another refresh command, and so on. Because all I have to do is refresh all the rows within 64 milliseconds. So now this is called as a TRFI, refresh interval. There is a 7.8 microsecond gap will be there between every pair of refresh operations. And that 7.8 microseconds is used for servicing processor side requests. So that processor side will not see significant delay in processing its request, because it's now interleaved. Processor request and the refresh both are interleaved and so on. This is one of the optimization techniques, but there are many refresh optimization techniques proposed in the DRAM literature and so on. But this is one of the important things. You need to do this, otherwise data will be lost. And the last one is the memory scheduling. We have multiple queues, read queue, write queue, and the command queues. We have to select the request from the read queue or a write queue. As I said previously, don't select the request one from read queue and the next from write and so on, because the write to read delay will be there. So generally what they do is typically they keep on reading from one queue, and they'll put a high watermark and a low watermark for each of the queue. Low watermark means once it is crossing below that, then you can switch over to the next one, and then so basically, like, you keep on, when the processor side requests are coming in, you keep on inserting into these queues. And anytime if any of the queue, the number of entries crossing the higher watermark, that means it is likely to be going to be full soon. Then you switch from one queue to another queue and start reading from that particular queue, and you just keep on moving. And once it comes to the low watermark, then you can say, okay, it is safe now to switch over to the other queue and then start reading. So you can switch between read queue and write queue using this high watermark and low watermark, so that you'll be servicing the request, same type of request, all reads are all writes, so that your write to read latency can be taken care. It can be like happening once in few operations and so on, so it can be amortized, that cost. And also we can exploit the localities and so on, and accordingly we'll schedule the requests and convert that into commands, and commands can be given to the corresponding command queues. And from there, the command scheduler is going to select. Again, here they can use FRFCFS, first ready, first come, first serve, right? Among all the commands which are ready, you can see which one is the oldest one, and then select that one. Because even though you have a command at the head of the command queue, but that command cannot be scheduled immediately, because we issued a previous command and you have to wait for some amount of time to issue this particular command. A simple case is I have issued and now act is there. I cannot immediately issue act. I have to wait for some amount of time. So you have to see which are the commands that are ready. From there, you can select the first one which came among all this. That is actually, this is one of the effective technique in the memory scheduling policies, FRFCFS, or otherwise you can simply use a round robin. Just go ahead with each of these queues one after another and so on. Different techniques are there and so on. But these are also going to determine the overall effectiveness of the memory controller. So scheduling, address mapping, refreshing, page management policies, all these are actually going to determine the overall effectiveness of your memory controller, and which in turn is going to determine the overall performance of your the system, because ultimately the data is going to be coming from the memory. Okay, and I'll just take a couple of minutes and I'll show you the DRAMs, right? So we are considering DDR4, but we came from SDR to DDR0, DDR1, 2, 3, 4, and so on. So SDR is a single data rate. That means when there is a memory cycle, in that memory cycle, single memory cycle, we will be reading data only one time. That is what is called a single data rate. And DDR is a double data rate. In your memory cycle, you have rising edge and the falling edge, right? So first half of the cycle, you read the data, and the second half also you read the data. That means in a single cycle, you will be reading 2 times. That is what is called a DDR. And all the current, the JEDEC standards are typically following this DDR. And if you see here, from SDR, when you go to DDR, memory side, if you see the process, memory technology, frequencies are not much improved. But so in the DDR, because they are double pumping every cycle 2 times, they are reading the data and so on, effective bandwidth is doubled compared to the SDR part. Then when they went to DDR2, where actually they have like, so reading double, because this is mainly because of you have a prefetch of 4, which is nothing but you have memory arrays, 4 arrays put together, and when you give a command, all these 4 arrays are going to read 1 bit of data and so on. If you have more planes parallelly, and they can supply more amount of data. In the DDR, they put actually 2 planes, 2x x2 device, and DDR2 they can say 4x, and DDR3 they can say 8x device. That means 8 planes are put together and then can supply the data and so on. So with that, and also their IO circuitry, they're clocking with a higher frequency, but also actually added to the improved memory bandwidth and so on. But after that, in the DDR3, they've not gone for 16x device and x16 device, but rather what they've done is they consider bank groups, and each bank group is having x8 device type of thing. And you can send now requests to 2 different bank groups, and they can supply the data in pipeline fashion and so on. And so this is what the DDR. And again, if you see, even in the DDR4 also, the memory array frequency is not much improved. But if you compare to the SDR, the overall memory bandwidth is significantly improved. That is because of this prefetching, multiple planes put together inside a DRAM bank, and reading in a pipeline fashion and parallel fashion and so on. Because of that, we are actually getting a significant improvement in the overall bandwidth. And that is what this graph, the same thing. You can find the details from this Synopsys website. So the frequency with which a DRAM array is working is not much improved, but the bandwidth is significantly improved. That is because of you added this prefetching, and you have this double pumping, and IO buffers are clogged with a higher frequency and so on. Because of all these things, you are able to extract a better performance or the better bandwidth from the memory and so on. In spite of all these things, still the processors are wanting the data at the higher rate and so on. That is where like we are considering this 3 levels are in. Sometimes we are also considering a 4th level of cache and try to exploit the locality available in the applications and so on. Okay. And these are some of the simulators you can find, and you can, if you, whatever the techniques we discussed, those things you can implement in these simulators. A ramulator from CMU group, Unur Mutlu's group, and RAM Sim2, which is like the authors of the memory systems book, Bruce Jacobs, their team, University of Maryland. So they have actually designed this RAM Sim2. And also you have this USIM from Utah, and also DR Sim and so on. So there are open source simulators you can, and easy to work with. These are like not a lengthy codes and so on. The simple functions are there. You can easily understand, and then you can work on it if someone is interested in understanding the internals of the DRAM memory. Okay. So that's it from my side. But actually now, yeah, it's a 3:22. How much time you have? Because I thought of giving a brief introduction about memory consistency, but I'm not sure whether we can do that now.
So Madhu, we have time till 3:30, but of course we can take a few more minutes, but again, it's up to the audience.
Yeah. So if they're okay, then maybe I'll just briefly introduce. Otherwise, like I'll wind up here. I have a couple of examples to explain this memory consistency, and I'm not going to go to all this, the TSO and so on. Maybe a sequential consistency part I can just explain. If they're okay, otherwise like...
yeah, it's fine with me at least. Like, so other people can also chime in, but...
Okay, then maybe I'll just quickly start. But it is actually, it's an interesting, the examples are very interesting, and we can just go through that. You will not get bored. Right. So again, so now we switch the gears. So we previously discussed the DRAM memory and so on. Now also in the morning, I think you had a class on cache coherency and shared memory systems, where the data can be replicated in multiple places, and you have to ensure that the data is coherent, and you have the invalidation based or update based protocols and so on. But this is another aspect. with the shared memory system. Typically, any shared memory multiprocessor system, if you are working with, there are three important issues. One is coherency, the other one is consistency, third one is synchronization. When multi-thread applications running on a shared memory system, how do we synchronize the things? That is what the synchronization is going to say. And the memory consistency say how the programmer is viewing when the threads are interacting with each other and so on, and how they perceive the memory, and similarly hardware, how it is implementing. That is what is discussed in memory consistency. And coherency is how do we ensure that the data is consistent or coherent. Let me take you the first example. Let us consider a two-core system, core 1 and core 2. And we have a simple piece of code. As a programmer, you have written this code. And what is your expectations? What are you expecting at the end from R1 and R2 registers? Core 1 is executing two store operations, storing new into data and flag is set. And core 2 is performing reading the flag into R1. And it says if R1 is not equal to set, go to L1. That means it's a loop, infinite loop. And only when the condition is true, that means if a condition false, that means if R1 is equal to set, then we'll be loading data into R2. So as a programmer, if you write this, what is your expectation? Expected values for R1 and R2. Memory consistency is mostly like all these things. Basically, as a programmer's point of view, what is there, but whether underlying hardware is implementing whatever the programmer's intuitions and so on. That is what basically the idea about the memory consistency. What do you expect in R1 and R2? Do you expect set and new is fine, right? For example, S1 is executed and then flag is executed. So once flag equal to set, the condition is false, then automatically it comes out of this B1. Then L2 load will be, second load is executed. Once second load is executed, data equal to new will be already there. So R2 is going to get new. So it means set and new is not a problem. Everyone expects set and new. But is it possible to get set and 0? Initially, we are considering data equal to 0. And is there a possibility of getting set and 0? That means R1 is going to get set and R2 is going to get 0. Is it possible under any condition? Any idea? No one is answering?
No, sir, no idea.
No idea. Okay.
It cannot be 0, right? Like
it cannot be 0. That's what the programmer always thinks. But the underlying system will do something. Because we already discussed in the morning, for example, in our class also, right? The superscalar processing. What we said is like, okay, if the instructions are independent, we can just execute in out-order fashion, right? And we also have the store buffers and so on. Here, S1 and S2 both are independent. Two different loads, two different operations, right? The store operation to two different locations and so on. They're not dependent. I can just rearrange, right? And once I rearrange, then flag S2 may be executed first compared to S1. Now, if that is the case, once flag equal to set, then this condition is false. Then automatically L2 can be executed on core 2. And then you are going to get 0. But the programmer's intuition is, anyway, he thinks that, okay, I write second store after first store. So first store anyway has to execute, then only second store. But underlying system may not think so. And underlying system, because of this hardware optimizations to extract more and more performance, it may be rearranging some of these instructions and executing in that different order. You have no control on that. Now, to complicate the things, we'll also consider another example. Tell me what is going to happen here.
just to clarify,
Again,
to clarify, you're asking about after execution, or you're asking about, I mean, at what point are we talking about here?
Right. So, for example, you have this piece of code, and then after that, you're using R1, R2 in some other places and so on, right? And what will be the value typically you'll get? for R1 and R2.
Yeah, but like I mean, I understand that this is
Ah.
I mean, the examples are supposed to, like, I don't know, like make us think, but yes, in reality, we're talking about after committing, right?
Right, but the thing is, like, you're not just waiting for till the store to be committed, right? Because that's the whole point we discussed in the morning also. Because stores are not critical.
Right. Okay.
And we just write it to store buffer and we say from the system point of view, okay, store is done. But we'll be writing that later. And if you write to store buffer, even if you have a cache coherency protocol, that will not be reflecting on the other core. The other core will simply looks at the data and the data will be there as the old value or whatever. Even if you write data equal to new here, right? But this is only written at the store buffer level and not to the actual cache or whatever. Only when you are writing to the cache, then cache coherency coming into picture. Then
Right.
you are going to read the wrong data.
Okay. Okay. Understood.
And similarly, the second one, R1, R2, X equal to new, Y equal to new, and R1 equal to Y and R2 equal to X. Initially, X, Y are 0. What are the values you can expect? So it can be S1, L1, S2, L2 in that order, or it can be S1, S2, L1, L2, or it can be S1, S2, L2 and L1, or any combination, right? Because you have no control on how the other core is going to execute operations. You may be executing your instruction in the program order, but the other core may come and then execute after you executed first instruction, and then the other core completes all these instructions or whatever. But whatever you consider, generally as a programmer, we think that, okay, it can be either new comma 0, 0 comma new, or it can be new and new. But it can also get 0 and 0. Again, this is complicating the things, right? Because when we write a load after a store, our idea is like it should be the 0, 0 cannot be happening. Because if R1 equal to Y, let us say if this is executed, S1, L1 executed before S2, L2, then you can say R1 equal to 0, fine. But the other case, because when L1 is executed, S1 is already done. So the other core R2, when it is reading, it should read value new, but it is reading 0. That is also again possible if you are using all these hardware optimizations. So this is actually complicating the things. Then a simple solution is, okay, if my underlying hardware is not maintaining the intuition set by the programmer, you disable all these hardware optimizations. That means don't learn superscalar or anything, whatever we discuss, and just go with in order scalar pipeline and so on. And no optimization, no write buffers, nothing, and so on. But if that is the case, then the performance will be degraded. We want the performance, at the same time, we want to maintain some intuition from the programmer's point of view. And that is where like we need some consistency model, which is effectively say that the programmer will view the memory in a consistent view. And if it is a unicore system, then basically what is going to happen is, if you have a memory hierarchy in a unicore system, processor will be there, L1, L2, L3 caches and main memory. So the thread running on the core 1, a single core, can see the consistent view of memory. It first checks in L1, then go to L2, then L3, and the cache and so on the main memory and so on. But if you have a multi-core system, some will have private caches, then the shared cache, then the memory and so on. And if I look at from core 1, the view may be different, and if I look at from core 2, the view may be different. And in addition to that, we have this store buffers and out of order execution. All these things also complicate the things. So it means we need to have some reference point. And once we set the reference point, the programmer uses that reference point and design his code with this particular analogy. And similarly, the hardware guys also take that reference point, and accordingly they'll come up with what optimization to be incorporated, which will not violate this reference point. That is the basic idea of this memory consistency. It's a specification of allowed behavior of multi-threaded programs executed on a shared memory systems. This is mainly for the shared memory, right? Because if you are not having a shared memory and then message passing systems and so on, you don't need a memory consistency point of view and so on. So this reference model will be used by both the programmer and the system designer. System designer is talking about the hardware or microarchitecture part and so on. And the programmer is writing the actual programs and so on. And based on this, programmer reason out, okay, if my store buffers are allowed, what are the possible outcomes I can expect? And accordingly, he'll write the remaining piece of code. And similarly, if the memory consistency model says like you should not use any store buffer and so on because it is going to give extra possible outcomes and that should not be allowed, then in that case, then the hardware system designer is going to disable all the store buffers inside, or he may disable all this out of order execution or whatever. Okay, so this is basically a reference point for both the programmers and the system designer, which look at the things and then accordingly they'll work. Okay, just I'll take 2 more minutes, and of course maybe I'll share these slides, and if someone has any, they can go through this, and then if they have any questions and so on, they can ask me later. Because of lack of time, I'm going to wind it up in another 2 minutes. And we already in the morning class, Professor Govindarajan has discussed the coherency. Once you have a coherency, do we require memory consistency? Yes, we do require memory consistency, because you may have coherency, but if I say I don't want a multi-core system with any caches, let's say in my multi-core system I have cores and the main memory only, no caches. Once there are no caches, there is no cache coherency. But even then, your coherency, memory consistency is required. The coherency, the goal is to ensure that the multiple caches in a multi-core system are going to maintain, if there is a same copy, they have to maintain the same copy, or one copy will be there and the others have to be invalidated and so on. And because it gives the flexibility to the programmer, that because the caches are not visible to the programmer, and then it can be the programmer gets the benefit because of the faster access and so on. But it ensures that the data is coherent in if there are replicated copies in multiple caches and so on. And the coherence always deals with only one block of data. If there is a block of data brought into core 1 private cache, and if the same data brought into core 2 private cache, and if core 1 is going to update, if it is an invalidation based protocol, I'm going to invalidate the block in core 2's private cache. But always it is just a single block we are dealing with. But the memory consistency is nothing to do with it. It's like, it can be, if you see the previous examples, maybe writing to some location here and then reading from some other location and so on. Because it is looking at the entire memory. And it is possible to implement a memory system without coherency or without even caches, but consistency is required, because a consistent view of the memory should be available with all the programmers, all the threads running on multi-core system. So in summary, cache coherency is not equal to memory consistency, but memory consistency can get the benefit from the cache coherency. If the underlying system is implementing cache coherency, we can actually make use of that. Especially if you want to implement a sequential consistency, we can actually make use of this MSI or whatever the protocols we implement for cache coherency that can be used to implement a simple or a rigid memory consistency model. And with this, I'm going to stop. So this is a sequential consistency idea is given by Lamport, and you can just go through this 4-line the sentence that gives you an idea about the sequential consistency. A multiprocessor system is sequentially consistent if the result of any execution is same as if the operations of all the processors were executed in some sequential order, and the operations of each individual processor appears in this sequence in the order specified by this program. Did anyone get this point? Don't worry, I'll just explain this only this particular sentence with an example, the same example whatever we considered previously. Let us say this is the example: S1, L1, S2, L2. Now, if my underlying system is implementing sequential consistency, whatever the results you are going to get for R1, R2 from this multi-threaded program, it should be consistent with any one of the possible outcomes from a sequential consistency. That means instruction can be executed in any order, but within a program, it should be executed in the program order. That means I should not have L1 executed before S1. If L1 is executed on core 1, then S1 is already executed. But I don't put any condition on when to execute S2 on other core, because other core, it performs its operations in any order and so on. So basically, this is one of the possible sequence, S1, L1, S2, L2. Then if this is the case, then my possible outcome is 0, new. Or I can execute S2, L2, then S1, L1. Then in that case, my outcome, possible outcome is new, 0. This is also valid sequentially consistent result. Or I can have interleaved S1, S2, L1, L2, or S2, S1, L1, L2. Anything is possible. New is the result. But if you want to get 0, 0, then you have to execute something like this. But this is actually violating. If you see here, S2, L2, right? So let us say we just execute S1 first, then L1. Then if I go to S2 and then L2. So 0, 0 means like one of these two should be reordered its execution, but that is not valid according to sequential consistency or according to the definition proposed by Lamport. And so as a result, this outcome is not sequentially consistent. So in other words, if my system is supporting sequential consistency, as a programmer, I can safely assume that this system is not going to generate 0, 0. And I'll just reason out only the remaining things, and accordingly, I'll write my rest of the code. But now once this is there, the hardware system designer also knows that it is actually sequentially consistent design. So he should not reorder any of these instructions and so on. So the sequential consistency is easy to implement, but actually most of the optimization we considered at the hardware level cannot be applicable here. We have to disable most of the things. And that is where like people propose many other things like relaxed consistency model. For example, Intel uses TSO, total store order, and multiple things are there. And if someone is interested, I can provide the related material, but I'll just conclude here. Just a brief introduction, but yeah. I have many other things also here, but yeah, you can just go through the slides afterwards. But this is basically memory consistency is going to give a consistent view for the programmer, and also it gives a reference point so that the hardware designers are going to see what optimization microarchitecture guys can consider what type of optimization can be incorporated inside.
Hello.
Yeah.
So you talked about this sequential consistency, but before that, the slide in which you were explaining all this possible combinations, my doubt wasn't in that particular slide only. So my doubt is like, though L1 can execute before S1, but the commit bit will be always in order, right? Like L1 will get executed before might get executed before S1, but the commit will be in order. So like S1 will be first committed, and then L1 will be committed. So the programmer only sees what is
no. The thing is like, because this L1 S1 is fine. Okay, within the program anyway they have to commit in the same order. But what do you do with the other code?
So right? Similar thing will happen with the other core as well. So like
no. So you're effectively like what you are saying is like, so within a program the instructions are going to be committed in the program order. That's not a problem, right? But the thing is like, it's not just only this particular order or whatever. Let us say if I have a store buffer, I just write the data into a store buffer. The store buffer of one core is not visible to the other core. And now the other core can go ahead and then it will see the memory in a different order, right? Because the consistency is lost now. Whereas a core one, if it writes some data into a store buffer, following operations can see the store buffer of that particular core, and it will see the data, different data. Whereas the other core, which cannot see the core one's store buffer, will see the memory in a different order. Now what is going to happen? Memory inconsistency is coming, right? Now different threads running on different cores will see the different values.
Yeah.
And that is actually going to create a problem. And that is where, like, when you say sequential consistency, disable the store buffers completely. But once you disable the store buffers, then the stores you have to perform before any load. And then that is actually degrading the performance from the architecture point of view. That's what we discussed in the morning. Now we need to, if you want to exploit that, then we have to come up with the store buffer. But once we come up with the store buffer, then we have to relax some conditions here. And that is where, like, from the sequential consistency, by relaxing some conditions, then we'll just go to a total store order. And if we further relax some conditions, then we'll just go to a relaxed consistency models and so on. There are many consistency models discussed and so on. But generally now what is happening is, like, if you want to use all the hardware optimizations, then you better go for relaxed consistency model. But once you have a relaxed consistency model, then it puts a burden on the programmer to reason out all possible scenarios. If it is a two threads running, then programmer can analyze. But if you have 10 threads running simultaneously, how do we analyze the behavior and so on, right? That is going to put a extra burden on the programmer too. Because ultimately, writing a program is one thing, but checking the correctness of the program, especially the multi-threaded programs, checking the correctness of the program which is executing correctly and so on is a tough task. And that is where people are actually using these reference points. And this is an interesting field of study. And there are lots of papers on this memory consistency and how to implement these things. And especially these days, people are coming up with this consistency models for this, the non-volatile based memories, emerging technologies, right, which are non-volatile in nature. And then how do we exploit those things, and persistent systems in which how do we implement these consistency models, and interesting things are happening. Maybe you can just refer to those things. But if you want some more material on the consistency, I can just provide it if you write to me. Yeah.
So just one more thing. So since we are now disabling this store buffers and all this, so basically we are not dynamically scheduling the memory instructions. We are only
right in the program order. Just simply the program order, even if it is a store operation and the following load which is independent and so on, we are just going ahead with the normal.
Okay.
But that is very rigid, right?
Yeah. So that's where I was coming. So because
right. So the thing is, like, programmer says, no, I don't want all these things headache and I want simple. Then the architects will say, like, okay, if you want, then I'll disable all these things, you will incur penalty. Now the question, the trade-off is again, so you need to maintain the correctness, but at the same time, you need to get better performance. And that is where, like, we need to come up with different methods now, intermediate techniques.
All right.
Yeah. But this is actually an interesting the topic, memory consistency. So you have to reason out all possibilities, and even the papers also talking about these proofs and so on, they're like very interesting. Unlike this cache coherence and so on. Cache coherence is also interesting, but yeah. But here, lots of things and difficult to understand, and yeah.
Okay, so and one more thing from the memory controller. So like, so there is something also called like error correcting codes.
Yes.
So
yes.
Like so could you like briefly like
no, error correcting codes typically, because when you are dealing with this memory and so on, right? So typically when the data is stored in this the DRAM, and if you are when you are reading, there may be some bit flips. And once there is a bit flip, because you need to actually, when you store the data, when you are retrieving, you have to retrieve the correct data. So that is where, like, we have this error correcting mechanism. Simple technique is like a parity bits. Every 8 bits, we are going to have one parity bit or something, right? And this is going to, when you read the data, you just read this parity bit, and accordingly, you just detect whether there is an error. Okay. And there are also other SecDed and few other things are there. But these are required if you are considering the memory for a server type of systems. If you are considering a laptop and a low-end systems and so on, generally DIMMs may not have the ECC capability. I'll just go back to this DRAM memory. I'll just show you one thing. Okay. So for example, if you see here, so this is an ECC based memory. So the middle, the chip, which actually takes care of this ECC part. And the DIMMs which are not supporting ECC, non-ECC based DIMMs, you will have even number of devices and so on. But this extra one is actually taking care of this ECC. And most of the time they'll use either parity, even or odd parity, or SecDed type of things. Not high complex error corrective mechanisms and so on.
Okay. So basically the chips which does not have this ECC capabilities were more vulnerable to rowhammer, like.
Yeah, rowhammer actually, yeah. So rowhammer basically, it's nothing to do with the. So what is going to happen is, like, let us say you have, for example, parity, right? You have an even parity information incorporated in your DIMM. But parity, effectively, if you have one bit flip, parity is going to detect, right? But if you have 2 bits flip, then parity is not going to say anything. And the rowhammer, what happens is, like, you keep on pressing one row continuously, and because of that, it is going to have an impact on the adjacent cells. And once it has an impact on the adjacent cells lose its charge. As a result, the data stored in that cell, if it is initially 0, it may be now represented as 1. If it is 1, it may be represented as 0. Because in the DRAM, what happens is like to optimize again the DRAM design, what they consider, some cells they consider as anti-cells and some cells they consider as true cell. A true cell, logic 1 is nothing but the capacitance in a capacitor should be above the threshold. Anti-cell is the charge in the capacitor should be below the threshold to be represented as logic 1. And that is the reason why, like when you have this DIM, some cells will be true cells, some cells will be anti-cells. And because of this repeated access of one particular row, then this has an influence on the adjacent row, and adjacent row leaks its charge, and because of that, the bits are going to be flipped. Now, let us say that particular row is having actually an address of a page table or something, which is actually you don't have any control, because let us say you are executing your application in user space and the page table is in the kernel space. But now what is going to happen is, if you keep on accessing this and you have now flipped the other bits, and because of that, you may be getting the access to that location, and then you just go there and then bring the data into your cache and then do the rest of the things and so on. So basically the idea of row hammer is repeatedly access a particular row which has an impact on the adjacent cells, and that is going to flip the bits. Once the bits are flipped, and depending on what data stored in that, then that is now going to point to something else, and from there you'll get an access. But actually, even though there are like almost 200 to 300 papers on row hammer, but if you want to actually come up with an attack using the row hammer, you have to do experiments in a very controlled manner, because you don't know which bits you are going to flip. Even when you perform a row hammer, you cannot say, okay, I'm going to flip bit 1 or bit 2 or something. No idea about what bits are going to be flipped. So that is the drawback with the row hammer. Even though it's an interesting work, but the side channel point of view, Spectre and Meltdown are the predominant attacks on microarchitectures or the processors than any other techniques and so on.
Okay, sir.
Yeah.
So, so about the resources for the memory consistency, should we like ask, like post it in the Discord server, or like should
Yeah,
we...
so I have maybe, yeah. So yeah, I'll just look at that and then I'll. So I'm going to send these slides, and the other things also I'll just share it. That's not a problem. Okay.
Sure, sir. Thank you.
Yeah, sure. Okay. So thank you all.